The faint scent of burnt magnesium lingers on the cold metal of my telescope's eyepiece, reminding me that even distant dust glows when heated. I sit on the porch, the night air thick with pine sap, and think of the thin, flat disks that spin around newborn stars. Those disks, thin as a sheet of paper, yet stretching for hundreds of astronomical units, hold the raw material for every planet we ever name. In their quiet glow, tiny grains of silicate and ice drift like specks of sand in a slow river. When two grains meet, static charge or a gentle bump can make them stick. Over thousands of years, those clumps become pebbles, then boulders, then bodies a few kilometers across. I find it hard to picture a pebble growing into a mountain without a hand to push it, yet gravity does the work in the quiet dark. The next step is called core accretion. A solid core, perhaps 10 times the mass of Earth, gathers surrounding gas. If the core reaches a critical weight, the gas rushes in, forming a giant envelope in a flash. This process can take a few million years, a blink compared to the star's lifetime, but long enough for the disk to lose much of its material. Not all disks follow the slow, steady path. In massive, cold disks, gravity can overwhelm pressure and cause a patch of gas to collapse all at once. That is disk instability, a rapid birth of a giant planet in a single, violent swoop. It bypasses the need for a solid core and can happen in a few thousand years, almost instantaneous in the scale of a star's life. Both roots, core accretion, and instability produce planets that begin their lives close to the star's equatorial plane. They share the same orbital direction, moving together like a fleet of boats in a calm bay. Yet even at birth, they are not safe from each other's pull. In the first few 100,000 years, the newborn planets still share a crowded playground. Their orbits can cross, and a close encounter may fling one outward or pull another inward. I sometimes hear the faint clatter of a distant meteor, a reminder that collisions are common in these early years. When a massive planet meets a lighter neighbor, the lighter one may receive a jolt, its orbit stretching into an elongated ellipse. If the kick is strong enough, the ellipse opens up, and the planet no longer circles the star. It becomes a wanderer, drifting through the galaxy untethered. The odds of such an exile depend on the system's mass distribution. A star with many giant planets, especially those packed close together, creates a chaotic environment where ejections are frequent. In contrast, a solitary giant, peacefully settled, rarely sends its siblings into the void. Observations of young star clusters show that disks disappear within a few million years. That disappearance marks the end of the main planet-building era. By that time, most of the solid mass has either formed planets or been ground down into dust that the star sweeps away. The timing matters. If a planet gains most of its mass early, before the gas clears, it can grow large enough to dominate its neighbors. If it waits too long, the gas is gone, and it remains a modest, rocky world, more easily tossed aside by a later arriving giant. I sometimes stare at the Milky Way and wonder how many of those faint points are planets that have lost their homes. We have caught a few rogue candidates, cold bodies wandering alone, their heat only a whisper from residual formation. Their detection is tricky. They hide in the dark, revealing themselves only when they pass in front of a distant star or emit a faint glow in the infrared. Our models suggest that for every star like our Sun, there may be at least one rogue planet drifting in the galactic halo. That estimate comes from simulations that count ejections over millions of years. Yet the exact number is still a guess. We lack a complete census. The process of ejection also reshapes the remaining system. When a planet leaves, the gravitational balance shifts, and the surviving planets may settle into new, more stable paths. Some may migrate inward, becoming hot worlds that skim the star's surface. Others may be flung outward, ending up in distant, cold orbits. Timescales vary wildly. core accretion can span 10 million years, while disk instability may finish in a few thousand. Dynamical scattering that leads to ejection can happen anytime after the planets have formed, often within the first few 100 million years, but occasionally much later when a distant star passes close by. I admit that our picture is still sketchy. The exact moment when a planet crosses the line from bound to unbound is hard to capture in simulations, and real systems may behave in ways we have not yet imagined. One thing is clear: the galaxy is not a static place. It is a restless sea of stars, each shedding material, each spawning planets, each occasionally losing a wanderer to the void. If you listen to the night, you can hear the soft rustle of leaves, the occasional hoot of an owl, and the faint hum of my old radio. Those sounds are reminders that even in the vast emptiness, small motions persist. The birth of a planet begins in a quiet, thin disk, but the story does not end there. Interactions, collisions, and the slow draining of gas all conspire to shape a planet's fate. Some stay tethered, some wander alone, and some may never form at all. When I glance down at the porch rail, a single drop of dew clings to the wood, catching the moonlight like a tiny lens. It sits there unmoving, while the universe above continues its slow, restless dance. The night air smells of damp pine, and the old metal latch on the gate creaks as the wind nudges it. I sit on the porch light humming like a tired watch, and let my thoughts drift toward wandering worlds. Planet scattering feels like a crowded ballroom where too many dancers push each other toward the exit. In a young system, dozens of newborn planets orbit close together, each tugging on the others with gravity's invisible hand. When one body gains a little extra speed from a near miss, the whole configuration can tip, sending the lighter planet spiraling outward. I sometimes wonder how often a planet simply bumps into another and is flung into the void. My mind pictures a marble striking another marble and rolling away across a dark floor. The mathematics behind those encounters are clean, but the reality is messy. A planet's path can change in a single, chaotic instant, and the resulting velocity may exceed the star's escape speed. When that happens, the planet leaves its home star behind, becoming a lone traveler in interstellar space. I find it hard to picture a world with no sun at all, drifting past cold clouds of gas, its night sky forever empty. Close encounters with passing stars add another layer of uncertainty. Imagine two stellar neighborhoods drifting past each other like slow ships in a fog. If a star passes within a few hundred astronomical units, its gravity can tug at the outer planets of the other system. The effect is similar to a stray gust knocking over a loose stone on a hillside. A planet that once traced a calm ellipse may find its orbit stretched, then broken, and finally released. Binary star dynamics are a special case of that stellar tug. In a pair of stars locked together, each planet feels the pull of two suns, not one. The combined gravitational field can be stable for some distances but chaotic for others. If a planet wanders into the region where the two stars' pulls cancel and then reappear, the planet may receive a sudden jolt. That jolt can be enough to push it past the system's escape velocity. I sometimes doubt whether we have captured all the possible configurations. Our simulations can only sample a fraction of the endless permutations. Supernova explosions introduce a truly violent kick. When a massive star ends its life, the core collapses, and a shock wave erupts outward at a fraction of the speed of light. Any planet orbiting that star feels an abrupt change in the central mass and a direct blast of material. The sudden loss of mass reduces the star's grip, while the blast can add a forward push. Together they can fling a planet outward, sometimes at speeds that carry it far beyond the remnants of the exploded star. The term natal kick is borrowed from neutron star studies, but it applies to planets as well. The kick is not a gentle nudge. It is a sudden shove that can alter a planet's trajectory dramatically. In some models, a supernova can impart a velocity of several kilometers per second to a nearby planet. That is enough to overcome the gravitational pull of even a massive binary system. I admit I cannot yet say how often such kicks succeed in freeing a planet. Observations are sparse. Statistical studies try to stitch together these mechanisms into a single picture. Researchers run thousands of simulations, varying planet masses, orbital spacings, and stellar encounter rates. The output often shows that a few percent of all planets may be ejected over a star's lifetime. In densely packed systems, the ejection rate climbs, perhaps reaching 10%. In sparse, well-ordered systems, the chance drops to a fraction of a percent. The numbers feel both small and large, depending on the angle from which you look. One way to gauge the likelihood is to compare the number of free-floating planets we have actually detected. Microlensing surveys have spotted objects the size of Jupiter drifting alone, with no host star in sight. Those detections suggest that rogue planets may be as common as stars, or perhaps even more so. Yet the data are noisy, and the surveys are biased toward larger, more massive bodies. I sometimes wonder if we are missing a whole class of Earth-sized wanderers hidden in the dark. The role of the galactic environment cannot be ignored. In the dense core of a star cluster, close stellar flybys happen more often, increasing the odds of planetary ejection. In the quiet outskirts of the galaxy, such encounters are rare, and most planets remain bound to their stars. The Milky Way's spiral arms, moving like slow waves, can sweep clusters together, creating temporary spikes in encounter rates. The timing of those spikes may line up with periods of heightened ejection activity. It is tempting to link the two, but the evidence remains tentative. Even the shape of the galaxy's gravitational field matters. The Milky Way's disk exerts a gentle pull that can stretch planetary orbits over billions of years. This slow stretching can nudge a marginally bound planet over the edge, especially if other perturbations have already weakened its grip. The effect is subtle, like a stone slowly rolling down a shallow slope. I have no precise measure of how much this contributes to the overall ejection budget, but it cannot be dismissed. Observationally, the signatures of ejection are faint. A planet that has left its star will no longer show the periodic dimming of a transit, nor the wobble of radial velocity. It will instead appear as a cold, isolated body, perhaps reflecting a faint glow of starlight from distant suns. Infrared surveys search for such heat signatures, hoping to catch a rogue planet's residual warmth. So far, only a handful of candidates have survived scrutiny. The chemistry of a wandering planet may tell a story of its origin. If a planet retains a thick atmosphere, its composition could hint at the type of star it once orbited. Heavy elements like carbon and oxygen might betray a formation around a sun-like star, while a dearth of certain gases could suggest a birth near a massive, short-lived star. We have not yet measured such details for any free-floating world, but future telescopes may make it possible. I suspect we will learn more about the past lives of these nomads than about their present journeys. One lingering question is whether ejected planets can host life. Without a stable source of heat, a planet would freeze over, its surface turning to ice. Yet internal heat from radioactive decay or a lingering core could keep subsurface oceans liquid, much like Europa's hidden sea. If a planet carries a thick atmosphere, greenhouse gases might trap enough warmth to maintain a thin habitable zone beneath the clouds. The idea feels speculative, but it is not impossible. I am hesitant to claim any certainty. The interplay of all these mechanisms, scattering, stellar flybys, binary dynamics, supernova kicks, galactic tides, creates a complex web of possibilities. Each mechanism can act alone or in concert, amplifying the chance of ejection. A planet might first be nudged by a neighbor, then later receive a gentle tug from a passing star, and finally be catapulted by a supernova blast. The cumulative effect can be larger than any single event. It is a reminder that the universe rarely follows a single, tidy script. Models that try to capture this web must simplify. They often treat planets as point masses, ignore atmospheric drag, and assume smooth stellar motions. Real systems are messier, with gas disks, debris, and magnetic fields all playing roles. The simplifications are necessary, but they also limit how well we can predict actual ejection rates. I sometimes feel the models are like a map drawn on a napkin, useful for a quick glance, but missing the fine detail. Future observations will sharpen our view. The upcoming generation of space telescopes will be able to detect colder, smaller rogue planets through direct imaging. Ground-based surveys will improve microlensing statistics, giving us a clearer census of free-floating worlds. At the same time, better measurements of stellar motions in the galaxy will refine our understanding of encounter frequencies. Each new data point will tighten the constraints on our theories. I look forward to the day when the numbers stop feeling like educated guesses. In the meantime, the picture that emerges is one of constant motion. Stars are not isolated islands. They share space, occasionally brushing past each other, sometimes exploding, sometimes simply aging. Their planets feel those changes, sometimes staying put, sometimes being tossed like stones from a shaking hand. The universe, in its vast quiet, is full of these subtle shoves and sudden throws. It is a place where gravity can be both a gentle clasp and a fierce flinger. As I stare at the dark sky, the faint hum of the porch light blends with the rustle of leaves. I think of a planet, perhaps the size of Earth, drifting alone, its night sky forever empty, its surface bearing the scars of a violent departure. The thought is both humbling and unsettling. I cannot claim to know how many such wanderers exist, nor exactly how each was set free. The answer remains out there, waiting for a patient eye. The night deepens and the scent of pine grows stronger, grounding me to this porch. My mind drifts back to the mechanisms that can send a world on a solitary trek. Each process, scattering, encounters, binary pulls, supernova kicks, adds a piece to a puzzle we are still assembling. The puzzle is large, the pieces irregular, and the picture incomplete. A moth lands on the porch rail, its wings pausing for a breath before it lifts again. A thin film of dew clings to the old metal latch as I turn the telescope's focus knob. The faint hiss of the motor, a reminder that even in darkness we keep listening. Tonight the sky is a quiet ledger of shadows, and I'm trying to read a page that never shows its name. Rogue planets, those lonely wanderers that drift without a sun to warm them, do not shine like the familiar worlds we map. They hide behind the night's plain veil, and we have learned to catch their brief fingerprints. The first trick we use is called gravitational microlensing. Imagine a distant star as a lantern, its light traveling straight toward us. When a massive object, even a planet the size of Earth, slides across that line, its gravity bends the light just enough to make the star appear a little brighter for a short moment. The brightening is tiny, lasting from hours to days, but it follows a shape that tells us something is passing in front of the star. I have watched many of those light curves on a flickering screen, each rise and fall a whisper of a hidden mass. The curve's peak tells us the lens's size, while the duration hints at its speed. When the curve is smooth, we suspect a single object. A wobble inside may betray a moon or a binary pair. But microlensing is a gamble. The alignment must be almost perfect, and the event cannot be repeated. We set up wide-field cameras to watch millions of stars at once, hoping that one will stumble into the right spot. When it does, the data rushes in and we sift through it like a miner panning for gold. A second method leans on heat. Even a planet adrift in cold space retains some internal warmth, a faint glow in the infrared. Our eyes cannot see it, but a sensor tuned to longer wavelengths can. The Wide-Field Infrared Survey Explorer, WISE, spent months circling Earth, its detectors feeling the gentle warmth of objects that emit little visible light. WISE cataloged countless points of infrared light, many of them distant galaxies, some nearby brown dwarfs. Among them, a few glimmered without a nearby star to explain their heat. Those were the first candidates for rogue planets. The survey's all-sky reach let us compare the brightness at different infrared bands, and a cooler object that still shines in the longest band fits the profile of a free-floating world. Euclid, a newer mission, adds sharper eyes and a broader reach. It looks not only for the faint heat but also for the subtle stretch of background galaxies caused by a planet's gravity, a kind of microlensing on a larger scale. By combining Euclid's infrared maps with its visible light images, we can cross-check whether a dim spot is truly a cold wanderer or just a distant, dusty galaxy. Both approaches, microlensing and infrared detection, feed a larger picture. We cannot count each rogue planet one by one, they are too few and far between. Instead, we build statistical models. We ask how many microlensing events of a certain shape we saw, compare that to the total number of stars monitored, and infer how common free-floating bodies must be. The same goes for infrared surveys. We tally all objects that fit the temperature profile, subtract the expected number of brown dwarfs, and the remainder hints at the rogue population. These numbers are rough, like trying to guess the size of a forest by counting a handful of fallen leaves. The models depend on assumptions about how bright a planet stays after its star dies, how fast it moves through the galaxy, and how many low-mass stars hide in the background. I sometimes find it hard to picture the exact shape of that hidden distribution, and the math can feel like a maze with missing walls. Confirming that a candidate truly roams alone is a stubborn task. A faint infrared source could be a distant star cloaked by dust, not a planet. Microlensing events can be mimicked by binary stars or compact objects like white dwarfs. To separate the wheat from the chaff, we need follow-up observations. One way is to look for motion. A rogue planet close enough should shift its position against the background over months or years. By revisiting the same patch of sky with high-resolution infrared cameras, we can measure that drift. If the object moves at a speed consistent with nearby galactic motion, we gain confidence it is not a far-off galaxy. Another check is parallax. Observatories placed far apart Earth and a space telescope, for instance, see the same object from different angles. The slight shift in position can tell us its distance. If the distance comes out to a few hundred light-years, the object's faint glow is more likely a planet than a distant galaxy. Even with these tools, ambiguity remains. Some candidates sit at the edge of our detection limits, where noise and signal blur together. We sometimes have to accept that a handful of objects will stay in the gray zone, their status forever a question mark. What we have learned, however, is that rogue planets are not rare curiosities. Early microlensing surveys suggested there could be as many free-floating worlds as there are stars in the Milky Way. Later infrared work refined that picture, indicating perhaps a few per star, but with a wide spread in mass. The truth probably lies somewhere between, with many Earth-size wanderers and fewer giant ones. The existence of these lonely bodies reshapes how we think about planet formation. If planets can be tossed out of their birth systems, then the architecture of planetary families is more fluid than a tidy set of orbits. Collisions, close passes, and the tug of massive stars can all fling a planet into interstellar space. Some may even form on their own, gathering gas and dust in the cold outskirts of a molecular cloud, never knowing a star's warmth. Our tools keep improving. New telescopes with larger infrared arrays will see fainter heat, while next-generation microlensing campaigns will monitor more stars with finer time resolution. The hope is that the statistical fog will thin, letting us count rogue planets with clearer certainty. Yet, as I sit here, the porch light humming low, I am reminded that each detection is a brief handshake across a gulf of emptiness. We catch a flash, a faint warmth, a tiny wobble, and we label it a planet that drifts alone. The universe does not announce these meetings. We have to listen, watch, and sometimes accept that the answer will stay just out of reach. The night air carries the scent of damp pine, and the telescope's motor clicks a steady rhythm. In the distance, a faint infrared dot sits on the screen, its glow steady, its story still half told. The metal case of the old spectrograph feels cold against my palm, its rim still bearing the faint imprint of a night-long stare. I pull the lid back and let the dim porch light spill over a stack of data sheets, each one a whisper of a planet that never saw a sunrise. Rogue planets, those lonely wanderers that drift without a star, show a spread of sizes that makes me raise an eyebrow. Some are barely larger than the moon, their mass measured in fractions of Earth's weight. Others swell to the bulk of Jupiter, pulling the surrounding gas into a thick, invisible veil. The catalog we have today lists a handful of objects with measured radii, but the numbers are sparse, like pebbles on a dark beach. When we plot mass against radius, a pattern emerges that feels almost too neat. Below about 2 Earth masses, the radius grows slowly, suggesting a solid interior of rock and metal. Above that, the curve steepens, hinting that a layer of gas begins to dominate the bulk. It is a reminder that gravity, even without a star's heat, still decides what a planet can hold. I find it hard to picture a planet the size of Earth, floating in the black, its surface never warmed by sunlight. Yet the equations say a rocky core can keep a thin veil of gas if the gravity is strong enough. The gas would be pulled inward, compressed, and held close, much like the thin air we feel at high mountain passes. The big rogues, those with masses near that of Saturn, behave differently. Their gravity is so strong that they keep a deep envelope of hydrogen and helium, the same ingredients that fill the outer layers of the gas giants we see around other stars. In those cases, the lack of a star does not strip the atmosphere. Instead, the planet's own heat, left over from its formation, may keep the gases from freezing out. We do not have a clear picture of how long that internal heat lasts. Models suggest that a massive planet could stay warm for billions of years, slowly radiating away the energy it stored when it first coalesced from a cloud of dust. But without a star's steady input, the cooling curve is steeper, and the outer layers may turn to ice clouds much sooner than we expect. One way to test this is to look for clouds that form high in the atmosphere. On Earth, clouds are water droplets, but on a cold rogue, methane or ammonia could condense into fluffy layers that scatter any stray light that passes nearby. If a cloud deck forms, it would make the planet appear brighter in reflected light, even though it never sees a sun. Observations with infrared telescopes have caught a few faint glows that could be such cloud layers. The signal is weak, and sometimes the noise of the instrument looks like a cloud itself. I sometimes wonder whether we are chasing shadows, but the pattern repeats enough to keep the question alive. Comparing these free-floating bodies to planets that orbit stars helps us see what the star does for a planet's makeup. A bound planet that sits close to its star often loses its lighter gases, leaving a rocky core stripped of most atmosphere. A rogue of the same mass, however, may retain that gas because there is no solar wind to blow it away. On the other hand, a planet that spends its life far from its star can keep a thick atmosphere simply because the stellar heat never reaches it to drive escape. The balance of gravity and temperature decides the fate of the gases, not the presence of a star alone. That is a subtle point that many models still miss. The composition of the interior also matters. A world rich in iron will be denser, pulling its atmosphere tighter. A planet with a larger fraction of water ice may have a lower overall density, making it easier for gases to drift away. Some rogue planets might be half rock, half ice, a mixture that could melt internally if enough heat remains. If a rogue has a substantial amount of radioactive material, the decay could provide a steady trickle of heat, keeping a thin layer of gas alive for eons. This internal furnace is a quiet engine, humming beneath a cold crust, and it may be the only source of warmth for a planet that never sees a sunrise. We have only a handful of direct measurements, so much of what we say rests on inference. The mass of a rogue is often derived from the wobble it causes in a nearby star's motion, even though the star is not its host. That indirect method leaves room for error, and I sometimes feel the numbers are more guesswork than fact. The radius, when we can measure it, comes from a brief dip in brightness as the planet passes in front of a distant star, a microlensing event that lasts a few hours. The data are noisy, and fitting a curve to a flicker can feel like trying to read a story in a storm. Because of these limits, the picture we paint is patchy. Still, the trends we see line up with what physics predicts. Larger mass, larger radius, thicker envelope. Smaller mass, denser rock, thinner or no envelope. The variety is real, even if the exact numbers are fuzzy. One intriguing idea is that some rogue planets could host thick, high-altitude clouds made of exotic compounds, like silicate particles that form on hot gas giants. In a cold environment, those particles would settle, but if the planet retains enough heat, a permanent haze could linger, giving the world a permanent, pale glow. If such a haze exists, it would affect any future attempts to study the planet's surface. The light we might catch would be filtered through layers of particles, much like looking at the sun through a dusty window. That makes interpreting spectra a careful task, and we must keep our expectations modest. The comparison with bound exoplanets also shows that many of the same processes are at work. A planet that migrates inward toward its star can lose its envelope, becoming a stripped core, while a planet that is ejected from its system may keep the envelope it had at the moment of ejection. The ejection itself is a violent event, a close encounter that flings the planet into the dark. Those violent births may also heat the planet, at least for a short time. The shock of being tossed out can melt the outer layers, perhaps creating a temporary magma ocean. If that ocean releases gases, it could add a fresh coat of atmosphere that later settles into a stable layer. We do not know how common such events are. Simulations suggest that in a crowded young system, a few % of planets may be tossed out, but the numbers depend on many uncertain factors. That uncertainty makes each new rogue detection feel like a small clue in a larger puzzle. In the end, the diversity of rogue planets mirrors the diversity we see in bound worlds. Some are tiny, solid, and cold. Some are massive, swathed in thick gases, perhaps with clouds that never melt. The lack of a star does not erase the physics that shapes them. It simply removes one of the forces that usually dominates. I sit back, listening to the night insects, and think of a planet drifting alone, its surface never warmed by a sunrise, its atmosphere held by the pull of its own mass. The porch light flickers, casting a thin line across the old spectrograph's glass. The line catches a speck of dust that settles, motionless, on the edge of the lens. The night air smells of damp pine, and the old metal railing under my fingers feels colder than the sky. I sit here, a lone watcher, and think about planets that drift without a sun. Rogue planets are not lit by a star, so their surface warmth must come from inside. The idea sounds odd, like a campfire hidden beneath a blanket of snow. Yet physics allows several ways for a world to keep a low glow. First, there is radiogenic heating. Certain atoms, uranium-238, thorium-232, potassium-40, decay slowly, releasing particles that turn into heat. On Earth, this process adds a few tenths of a watt per square meter to the surface budget. On a wandering planet, the same decay can be a larger fraction of the total heat flow because there is no solar input to drown it out. I find it hard to picture a whole planet warmed by the slow ticking of atomic clocks. The decay rates are tiny, but they never stop. Over billions of years they add up, like a drip that eventually fills a bucket. If the planet holds a lot of heavy elements, the internal furnace can stay warm for eons. Next comes the leftover heat from formation. When a planet coalesces from dust and rock, gravity pulls material together, and the falling mass converts potential energy into heat. That heat spreads through the body, raising the temperature of the mantle and core. In the first 100 million years, the planet may glow like a faint ember. The problem is that this primordial heat leaks away. A planet without a star loses heat to the void, and the rate depends on its size and composition. Larger worlds lose heat more slowly because they have more volume than surface. Smaller ones cool faster, like a stone dropped into cold water. Scientists use thermal evolution models to track that cooling. They start with an initial temperature, add radiogenic heat, and let the planet radiate energy into space. The equations are simple in form. Heat capacity times temperature change equals heat sources minus heat loss. But solving them over billions of years needs a computer. The models show a wide range of possible outcomes. One surprising outcome appears when two rogue planets orbit each other. Their mutual gravity can stretch and squeeze each body as they move along an eccentric path. This tidal flexing converts orbital energy into heat, a process called tidal heating. It is the same trick that keeps Jupiter's moon Io volcanically active, even though the moon is far from the sun. In a binary rogue pair, the tidal forces can be strong if the orbit is tight and eccentric. The heat generated can rival or exceed radiogenic heating, especially for rocky worlds with a flexible mantle. The models predict surface temperatures that stay above the freezing point of water, even without any sunlight. I sometimes doubt whether such tight rogue pairs survive long enough. Gravitational interactions with passing stars or the galactic tide can pull them apart. We don't really know how common they are, but the physics allows the possibility. Putting the pieces together, the surface temperature of a rogue planet becomes a balance. Radiogenic heat provides a steady low-level input, primordial heat adds a fading burst, and tidal heating can add a sudden boost if the conditions are right. The total may be only a few degrees above absolute zero, or it may reach a few tens of Kelvin. For comparison, Earth's average surface temperature is about 288 K, thanks to the sun's steady shine. A rogue world warmed only by internal sources might sit at 30 K to 70 K, similar to the temperature of distant moons in our own system. That is colder than a freezer, but still warmer than the blackness of interstellar space, which hovers near 3K. If a rogue planet has a thick atmosphere of hydrogen or methane, the greenhouse effect can lift the surface temperature a bit higher. The atmosphere traps the infrared radiation that the interior emits, much like a blanket keeps a child warm. But without a star, the blanket can only hold in what the planet itself makes. Measurements of such worlds are scarce. We have only a handful of candidates spotted by microlensing surveys, and none have been studied in detail. The data give us mass estimates, sometimes radius, but no direct temperature reading. The models fill the gap, but they rest on assumptions about composition and history. There is also the question of heat transport inside the planet. In Earth's mantle, convection carries heat upward in slow, rolling currents. In a cold rogue planet, the mantle may be mostly solid, and heat moves by conduction, a much slower process. That slows the loss of primordial heat, extending the warm period. I sometimes wonder whether life could cling to such a world. If liquid water exists beneath an ice shell, warmed by tidal heat, a hidden ocean might persist. The same idea fuels speculation about Europa and Enceladus, moons that sit far from the sun yet host subsurface seas. A rogue planet could host a similar ocean, insulated by a thick ice crust. But the lack of sunlight removes photosynthesis, the engine that drives most ecosystems on Earth. Any life would have to rely on chemical energy, perhaps from reactions between rock and water, or from the slow decay of radioactive elements. That would be a very different biosphere, one we can only imagine. The biggest uncertainty lies in the amount of radiogenic material a rogue planet carries. Stars forge heavy elements, and planets inherit whatever their parent star's composition provides. If a planet formed around a metal-rich star, it may hold more uranium and thorium, boosting its internal furnace. If it formed around a metal-poor star, the furnace may be dim. Another unknown is the initial orbital configuration of binary rogue pairs. Did they form together in a dense cluster and get ejected as a pair, or did they capture each other later? The capture scenario would likely produce a wide, low-energy orbit, yielding little tidal heating. The ejection scenario could lock them into a tight dance, generating more heat. Thermal evolution models try to capture these variables by running many simulations with different inputs. The output is a spread of possible surface temperatures, often shown as a band on a graph. The band can be wide, reflecting our lack of precise data. One thing we can say with confidence is that a rogue planet will never reach the warmth of Earth's surface without a star. Even the most generous internal heating falls short of the 260 Wm2 solar constant that Earth receives. The gap is huge, like comparing a candle's glow to a floodlight. Yet the gap does not make rogue planets irrelevant. They are laboratories for physics under extreme conditions. They test our ideas about heat flow, planetary interiors, and the limits of habitability. Observing them forces us to refine our models, which in turn improves our understanding of planets that do orbit stars. Future telescopes may catch the faint glow of a rogue world in the infrared, where its own heat radiates. A detection would let us compare the measured temperature to the predictions from radiogenic, primordial, and tidal heating. That would be a quiet triumph for the models that sit on my desk. Until then, I sit on this porch, listening to the night insects and let my mind wander to cold, wandering stones. I picture a planet drifting through the darkness, its core ticking away like a slow, steady drum, sending out a faint warmth that barely stirs the surrounding void. The last thought I cling to is the feeling of the railing's metal under my palm, a reminder that even in the coldest places, a small amount of heat can change the way we feel. A moth lands briefly on the porch light, its wings trembling, then it flies away into the night. The night air smells faintly of pine, and the old metal telescope sits cold on the railing. I stare at the thin line where the sky meets the dark, wondering how much ice can hide beneath a planet's skin. Ice shells are not uniform blankets, they thicken where gravity squeezes the crust tighter. A few kilometers of frozen water already feel like a solid stone under a foot. Pressure climbs 100 bar for every 10 kilometers of depth, turning the familiar ice I know into a strange, denser form. That change is shown in the water phase diagram, a chart that looks like a cracked window pane. At low pressure, ice is light and fluffy, but under the weight of a thick shell it shifts to ice VI or VII, each denser than the last. Those high-pressure phases melt at temperatures far above the surface freeze, opening a window for liquid water deep inside. I find it hard to picture a sea hidden beneath a crust as hard as basalt. Yet the math says a few hundred miles of ice can still trap heat enough to keep a layer of water liquid. The heat comes from two quiet sources: the decay of radioactive elements in the rocky core and the slow squeeze of tides. Radioactive decay is a steady ember, barely noticeable but never truly gone. Tidal flexing is more like a faint drumbeat, the moon's gravity pulling and releasing the shell over millions of years. Both sources together form an energy budget that, on paper, can sustain a global ocean. If the budget falls short, pockets of water may still exist where the crust is thin or where cracks allow heat to escape. Europa, that smooth, mottled moon of Jupiter, offers a first clue. Its surface shows ridges and cracks that look like frozen riverbanks, hinting at a restless layer below. Enceladus, Saturn's tiny geyser-spouting moon, erupts water vapor straight into space, a clear sign that liquid exists just beneath its icy skin. Both bodies are far from Earth, yet the patterns they display are simple enough to read with a modest telescope. The infrared excess we measure from distant worlds is another whisper of hidden warmth. When a planet radiates more heat than its star supplies, something inside must be generating that extra energy. Scientists have spotted this excess on a handful of distant ice-covered planets, suggesting subsurface oceans may be common. I sometimes wonder whether the excess is just a measurement error, a stray photon, or something real. We don't really know how thick the ice shells are on those far-off worlds, because we can't send a drill there. Models estimate shell thickness by balancing the outward pressure of the ocean against the inward weight of the ice. A thicker shell means higher pressure, which pushes water into those exotic ice phases that melt at higher temperatures. Thus, a planet with a very thick shell could still hold a liquid layer, provided its interior stays warm enough. Conversely, a thin shell may freeze the ocean completely if the heat source is weak. The balance is delicate, like a tightrope walker in a midnight storm. Even a small change in radioactive content can tip the scales. Some researchers argue that a thin crust would crack easily, letting heat escape and the ocean freeze. Others point out that cracks could also act as conduits, funneling warm water upward and keeping the sea alive. I'm skeptical of any single picture. The reality is probably a patchwork of both. Observations of Europa's surface show regions where the ice is only a few kilometers thick, next to areas that seem dozens of kilometers deep. Enceladus's south pole, by contrast, has a thin tiger stripe region that vents water, while the rest of the moon remains heavily iced. These contrasts teach us that ice shells can be wildly uneven, shaped by local heat and stress. If a distant exoplanet follows a similar pattern, its ocean might be a series of hidden lakes rather than a global sea. The phase diagram tells us that at pressures above about 1,000 bar, water can exist as a super-dense liquid, even at temperatures near 0 degrees C. That state is unlike any ocean we have on Earth, but it would still be liquid enough for chemistry. Chemistry, in turn, is the language life might learn to speak. We can only guess at the nutrients that could dissolve in such a deep, pressurized sea. If the rocky core releases salts and minerals, they could dissolve and circulate, providing the building blocks for microbes. But the thick ice barrier also blocks sunlight, so any life would have to rely on chemical energy, not photosynthesis. On Earth, hydrothermal vents host thriving ecosystems that never see a ray of sun. It seems reasonable that similar vents could exist on Europa or Enceladus, feeding a hidden biosphere. Yet the chemistry of high-pressure ice phases may lock away many of the elements life needs. We lack direct samples, so any claim about habitability remains speculative. The infrared excess we detect is a faint glow, a warm breath in the cold of space. It is measured by space telescopes that stare for weeks, counting photons that barely nudge the detectors. When the excess aligns with a planet that should be frozen solid, it raises eyebrows. One could argue that atmospheric gases, not an ocean, produce the extra heat. That argument holds weight for some worlds, but not for those with no obvious atmosphere. In those cases, a subsurface ocean becomes the most plausible source. The energy budget for such oceans is modest. We need only a few milliwatts per square meter to keep water from freezing. That amount is comparable to the heat flow from a single campfire, spread over a planetary surface. A campfire's glow can be seen from miles away. A planet's heat signature can be seen from light years away. Our instruments are just sensitive enough to catch that whisper. The quiet nature of this signal makes it easy to miss, much like a moth's wing beat in a storm. That is why many potential ocean worlds sit unnoticed in data archives. I sometimes sit here, listening to the crickets, and think about how many hidden seas we have yet to find. The idea that a frozen world can hide a warm interior feels like a paradox, but physics allows it. Pressure raises melting points, while internal heat raises temperatures. Together they carve out a narrow band where liquid can survive. If the band is wide enough, a global ocean forms. If narrow, only isolated pockets appear. Both scenarios could support life, though the latter would be more isolated and fragile. Future missions aim to drill through Europa's ice to taste the water directly. Until then, we rely on remote clues. The shape of the surface, the pattern of geysers, the glow in infrared. Each clue is a small stone we place on a path we cannot yet see fully. I am aware that my imagination fills gaps where data are thin. We don't really know the exact composition of the ice shells, nor the exact heat flow inside. What we do know is that water, pressure, and heat can conspire to keep a liquid layer alive beneath a frozen world. That possibility reshapes how we think about where life might hide in the cosmos. It also reminds me that darkness does not always mean dead. It can be a veil over hidden motion. The porch light flickers, casting a thin halo on the telescope's metal. A single grain of sand, caught in the wind, rolls across the wooden floor, pausing briefly before disappearing into a crack. The thin film of frost on the sensor's glass slides shivers when the night wind brushes it, a reminder that even a cold rock can hold a breath of chemistry. I sit here, eyes half closed, listening to the low hum of the power unit, and I wonder how life might cling to a planet that never sees a sunrise. First, we must ask what energy a rogue world can draw from. Without a star, the surface receives only the faint glow of distant starlight, far too weak to drive photosynthesis. Yet heat from the planet's own interior can leak outward, like the slow exhale of a sleeping giant. Radioactive decay of elements such as uranium, thorium, and potassium releases particles that warm the mantle, keeping the crust warm for billions of years. That warmth can melt pockets of ice, forming liquid layers beneath a frozen shell. In those hidden seas, chemistry can take over where light cannot. On Earth, similar places exist at the bottom of the deepest oceans, where black smoker vents spew hot water rich in sulfides. Microbes there harvest energy by oxidizing those chemicals, a process we call chemosynthesis. If a rogue planet hosts similar vents, its life would likely be built on the same principle. The key is a steady supply of reduced compounds, hydrogen, methane, sulfide, that can react with oxidants such as nitrate or dissolved oxygen. The planet's mantle can generate hydrogen by reacting water with iron under pressure, a reaction that has no need for sunlight. I find it hard to picture a whole biosphere built on that single trick, but the Earth's deep-sea ecosystems show it is not impossible. Those communities thrive on the heat of the Earth's core, converting a few joules per kilogram of water into the chemistry that sustains them. Their growth rates are slow, their cells tiny, their whole world a quiet, steady conversion of heat into life. On a rogue planet, the same slow pace would dominate. Metabolic rates would sit near the lower limits of what biology can manage. A single cell might need years to double, yet that is enough to keep a population stable if the environment remains unchanged. Stability is the next hurdle. Liquid water must persist long enough for evolution to take hold. On Earth, the deep ocean has stayed liquid for over 4 billion years, thanks to the planet's internal heat and the pressure that prevents water from boiling away. A wandering planet could keep a similar ocean if its core retains enough radioactive material. Models suggest that a planet the size of Earth, with a mantle rich in uranium, can keep a subsurface ocean warm for a few 100 million years, perhaps longer. That span is short compared to the age of the solar system, but it matches the time needed for simple microbes to appear, as our own record shows. The chemistry of such an ocean would be dominated by iron, sulfur, and carbon compounds. Iron oxidizing bacteria could take rust from the rocks and turn it into energy, while sulfate reducers would do the opposite, pulling electrons from sulfates to make organic molecules. The two groups could form a loop, each feeding the other, much like the cycles we see around Earth's vents. One might ask whether the lack of sunlight would prevent the formation of complex molecules like DNA. In the dark, radiation from radioactive decay can break bonds, but it can also drive synthesis. Laboratory experiments have shown that high-energy particles can splice simple organics into longer chains, a process that could happen in the thick water of a rogue world. Still, the step from simple chemistry to a self-replicating system is a leap we cannot fully map. We do not really know how many steps are needed, or whether a planet's chemistry could stumble across the right sequence without the nudging hand of sunlight. If life does arise, it would likely stay near the heat source, clinging to the walls of hydrothermal vents. The further you drift from those hot spots, the colder the water becomes and the slower the reactions. A gradient of temperature would create a thin habitable belt, perhaps a few meters thick, wrapping the planet's interior like a warm scarf. Energy pathways beyond heat are also possible. Cosmic rays, high-energy particles that travel through space, can penetrate deep ice layers, creating radicals that may serve as electron donors. On Earth's ice caps, such particles form tiny amounts of hydrogen peroxide, which some microbes can use. On a rogue world, the same process could provide a trickle of extra fuel, though it would be far weaker than the heat from the core. Another source is tidal flexing, if the planet has a large moon or passes close to a massive body. The repeated stretching can generate heat, much as it does for Jupiter's moon Io. However, most rogue planets wander alone, so tidal heating is likely rare. Putting these pieces together, the most plausible picture is a world where life lives in dark, pressurized seas, feeding on chemicals churned out by the planet's interior. The ecosystem would be thin, slow, and fragile, but it could persist as long as the heat source does. Compared to Earth's deep sea vents, the rogue planet communities would lack the occasional influx of organic material from surface runoff. They would rely entirely on the steady drip of chemicals from the mantle. That makes them more vulnerable to any change in the planet's radioactive inventory. If the core's heat wanes, the ocean could freeze solid, ending the biosphere in a quiet snap. Yet even a brief window of habitability could be enough for evolution to experiment. On Earth, life has shown a knack for finding niches in places we once thought impossible, inside rocks, under Antarctic ice, in the guts of whales. The same stubbornness could appear on a planet that never sees a star. We can test these ideas with a few tools. A probe that lands on a cold, dark world and drills through ice could measure temperature gradients and detect gases released from the interior. If it finds methane, hydrogen sulfide, or other reduced gases, that would hint at the chemistry needed for chemosynthesis. Spectroscopy from afar can also give clues. Anomalous amounts of certain gases in a planet's thin atmosphere, like methane without an obvious source, might signal biological activity. But without sunlight, interpreting those signals becomes harder and false positives are common. In the end, the picture remains sketchy. The physics of heat flow, the chemistry of reduced compounds, and the biology of slow metabolism all point to a narrow set of possibilities. I can imagine a world where life clings to a vent like a moth to a dim lamp, but I also know that many steps in that chain are still missing from our knowledge. So I sit here, the night air cool against my skin, the frost on the sensor growing thicker, and I let the idea settle like a slow drip of water into a deep pool. A faint click from the instrument's recorder marks the end of my thoughts, and the only thing left to notice is the way the frost catches the weak glow of the distant stars, turning each crystal into a tiny, silent mirror. The night air smells of damp pine, and the old tin can on the porch rattles as a stray wind brushes it. I lean back, eyes half closed, and let the quiet settle around the thought of planets that never found a sun. Rogue planets, worlds that drift alone, are not a myth. Surveys of microlensing events suggest that for every star we see, there may be one or more wandering planets hidden in the dark. If I take the most recent estimate, about 1.5 rogue planets per main sequence star, then the Milky Way could hold billions of these cold wanderers. That number feels huge, but the galaxy is vast, and the count grows with each new detection. Most of these free-floating bodies likely live in the thin disk, the same flattened region that hosts most of our bright stars. Their orbits are not tied to any single star, so they wander through the same spiral arms that we call home. A smaller but intriguing fraction drifts far above the disk, into the halo that surrounds the galaxy. In that region, the stellar density drops, yet the gravitational pull of the dark halo still holds them in loose, elongated paths. The distribution is not even. Near the galactic center, the crowded environment may fling planets outward, feeding the halo population. Out in the outer rim, the lower star density means fewer ejections, but the few that escape can travel for billions of years. Some researchers have asked whether these countless cold stones could add up to a noticeable fraction of the galaxy's mass. The answer is a cautious maybe. If each rogue planet weighs about 10 Earth masses, their combined weight could be a few percent of the total stellar mass. That few percent contribution is too small to solve the dark matter problem, but it does remind us that not all mass is luminous. The hidden weight of these planets sits quietly alongside the invisible particles that dominate the halo. I find it hard to picture a planet the size of Earth drifting through empty space, its surface forever frozen, receiving only the faint glow of distant stars. Yet that picture helps us grasp how little light they emit, making them almost invisible to ordinary telescopes. Because they emit almost no light, we must rely on indirect tricks. Gravitational microlensing, when a planet briefly magnifies a background star's light, has become our main tool. Each event is a fleeting flash, a whisper of mass passing between us and a distant star. The rate of these flashes tells us how many rogue planets lie along our line of sight. By counting them across many fields, astronomers infer the overall population. The method is noisy, but the trend is clear. There are many. Future surveys will sharpen the picture. The upcoming Nancy Grace Roman Space Telescope will monitor millions of stars with a cadence designed for microlensing. Its wide field of view should catch thousands of short events, each a clue about a wandering world. Ground-based projects like the Vera C. Rubin Observatory will also add to the tally, though their cadence is less suited for the shortest events. Still, Their deep images will help map where the free-floating planets cluster, if they do at all. Beyond counting, we can ask how these planets move. Simulations suggest that many were born in planetary systems and later ejected by gravitational tussles with giant neighbors. Others may form directly from collapsing gas clouds, much like stars, but never gather enough mass to ignite. If ejection dominates, then the rogue planet count tells us something about the chaos of young planetary systems. A high ejection rate would imply that massive planets often disturb each other, flinging smaller siblings into interstellar space. The presence of rogue planets also raises a quiet question for future travelers. A ship sailing between stars could, in principle, use a wandering world as a temporary stopover, a place to refuel or hide. The odds of finding one close enough, however, remain slim. Even a brief encounter would be a marvel. Imagine drifting past a frozen sphere, its surface etched with ancient craters, the thin atmosphere, if any, holding a whisper of gases. Such a sight would be a reminder that planets do not need a star to exist. Yet the practical challenges are great. Without sunlight, any landing craft would need its own power, and the cold would sap heat quickly. The lack of a magnetic field would expose travelers to cosmic rays, a harsh environment for long stays. Our models of galactic mass also need to consider these objects. When we calculate the rotation curve of the Milky Way, we assume most mass is in stars, gas, and dark matter. Adding a few percent of rogue planet mass nudges the curve ever so slightly. That nudge does not resolve the mismatch between observed rotation speeds and visible matter, but it does tighten the error bars. It also forces us to look more carefully at the low luminosity side of the mass budget. There is still a lot we do not know. The exact size distribution, whether most are Earth mass or many are smaller, Mars-sized bodies, remains uncertain. Microlensing is most sensitive to objects a few Earth masses, leaving the smaller crowd in the dark. If a large swarm of sub-Earth bodies exists, they could collectively hold a surprising amount of mass. Our current instruments simply cannot see them, and the theory of how they form is still shaky. Some scientists propose that a population of free-floating planets could seed life in unexpected ways. A wandering world might capture a passing comet, delivering water and organics, creating a brief oasis. The idea is speculative, but it reminds us that even the coldest places can hold surprises. The debate over whether rogue planets contribute to the dark matter puzzle reflects a broader tension in astronomy. We often fill gaps with the unknown, then later replace those gaps with measured facts. The process is slow, but it is steady. As new telescopes open their eyes, the count of rogue planets will rise, and their map across the galaxy will sharpen. Each new detection will be a tiny pin on a massive, invisible chart that we are only beginning to draw. I sometimes wonder whether a rogue planet could pass close enough to our solar system to be seen as a bright, moving point in the night sky. The chance is minuscule, yet the notion feels like a quiet joke the universe tells us. Even if we never see one directly, the statistical weight of their existence reshapes how we think about planetary formation. It tells us that the story of planets is not confined to tidy orbits around stars, but includes a wandering chapter. The next decade will bring a flood of data, and with it, a clearer sense of how many cold worlds roam between the stars. The numbers will likely still carry large error bars, but the trend will become unmistakable. In the meantime, the night remains still, the pine scent lingering, and the tin can continue its soft clatter. I glance at the faint smear of the Milky Way, wondering how many unseen stones trace silent paths through that pale river of light. The pine-scented wind brushes the old porch rail, and a moth flutters past the dim lamp. I lean back, the wooden boards sigh beneath me, and the night feels like a thin sheet of paper. Free-floating planets, objects that wander without a star, have become more than a curiosity. Their numbers, hinted at by microlensing surveys, now press on our textbooks like a stubborn knot. If they are common, the story we tell about how planetary families grow must change. First, the early years of a planetary system are not as calm as the solar system's quiet childhood suggests. Simulations show that massive bodies can stir the disk, sending smaller rocks into chaotic orbits. I find it hard to picture a newborn system where every planet sits politely in a neat ring. The reality seems more like a crowded dance floor where partners constantly bump into each other. One way to create rogue planets is to fling them out with a hard shove. When a protoplanetary disk is massive, several hundred times the mass of Jupiter, its gravity can dominate the motions of nascent planets. A giant planet growing fast can act like a wrecking ball, pulling on its neighbors until one is hurled beyond the star's reach. The disk's own weight, the pressure of gas and dust, adds a hidden hand that can accelerate the ejection. In some models, a single massive disk can launch dozens of bodies into interstellar space before the gas clears away. But our own solar system does not read like a wreckage site. The giant planets sit in relatively stable orbits, and the inner planets have survived for 4.5 billion years without being tossed out. This calm history places a constraint on how violent the early instability could have been. If a massive disk once surrounded the Sun, it must have been less massive than the disks that produce many free floaters, or the giant planets must have formed later, after the gas thinned. The absence of a large population of ejected bodies nearby suggests that the Sun's birth environment was gentle, perhaps a quiet corner of a stellar nursery. That gentle corner feeds back into how we think stars themselves are born. Star formation models often assume that dense clouds collapse into clusters where interactions are frequent. Yet the scarcity of ejected planets around Sun-like stars hints that many stars may form in looser groups, where massive disks can grow without being shredded by nearby stars. If the Sun's birth cloud was sparse, the disk could have lingered long enough to form the four giants without a massive ejection event. This picture nudges us to re-examine the balance between cluster density and disk mass in star formation theories. There is also a hint that other galaxies may hide reservoirs of these wandering worlds. Observations of distant galaxies show that star-forming regions can be far more massive than those in the Milky Way. If massive disks are common in those places, the number of free floaters could be orders of magnitude higher. Yet we have no direct way to count them beyond our own galaxy. The data are thin, and the models stretch thin as well. We don't really know whether the Milky Way is typical or an outlier in this regard. The presence of many rogue planets forces us to ask whether planetary systems are more fragile than we thought. In a crowded young disk, a planet's orbit can shift dramatically in a few 100,000 years, a blink in cosmic terms. A slight change in the disk's density can turn a stable orbit into a chaotic one, sending the planet spiraling inward or outward. If such shifts are common, the architecture we see today may be the survivors of a violent selection process. Consider the constraints that come from the timing of instability. If a system's giant planets become unstable early, within a few million years, there is still plenty of gas to damp motions, possibly preventing ejection. But if the instability occurs after the gas has gone, the planets have less resistance and can be flung far more easily. The timing, therefore, matters as much as the mass of the disk. Some researchers argue that the solar system's lack of ejected planets points to an early, gentle settling, while others claim a later, calm phase. I admit my own picture is hazy. The data leave room for both. Massive disks also affect the chemistry of the system. A thick veil of gas can trap volatile compounds, altering the composition of planets that form within. When a planet is ejected, it carries that chemistry into interstellar space, turning the galaxy into a pantry of exotic ices and rocks. If many such objects wander, they could seed other systems with material that would otherwise never leave their birth star. That feedback loop, planets shaping the chemistry of the galaxy, adds another layer to the puzzle. Comparing the solar system to the chaos seen in simulations, I sometimes wonder whether we are looking at a rare calm or a common quiet after a storm. The inner planets are tightly packed, yet they have avoided collisions for billions of years. Perhaps a gentle early history is more the rule than the exception, and the free floaters we detect are the outliers that escaped a harsher environment. Or perhaps we simply have not yet looked deep enough to see the quiet survivors hidden among the stars. The notion of unseen reservoirs in other galaxies also raises a practical question. Could some of the microlensing events we attribute to rogue planets actually be low-mass stars or brown dwarfs? The mass estimates are often uncertain, and the distinction blurs at the low end. If many of the detections are misidentified, the implied number of free floaters drops, easing the pressure on formation models. Yet the current trend leans toward a genuine surplus of planetary mass objects drifting alone. Star formation models must now accommodate a broader range of outcomes. Instead of a single pathway, disk forms, planets settle, system stabilizes, we need a suite of possibilities. Massive disks that eject, modest disks that keep planets, clusters that strip away material, and isolated births that let disks linger. This richer set of scenarios may explain why some systems host hot Jupiters while others keep their giants at a distance, and why some neighborhoods of the galaxy are peppered with wandering worlds. I sometimes sit on this porch and stare at the faint glow of the Milky Way, wondering how many of those pinpricks are actually lonely planets, drifting like ash in a cold wind. The night air carries the distant hum of crickets, a reminder that even in the vastness of space, small, ordinary sounds persist. If we accept that many planets are cast out, then the concept of a planetary system becomes more fluid. It is not a closed box but a porous vessel, exchanging material with its surroundings. The idea of a stable, isolated system may be more of a convenient shorthand than a hard rule. Future surveys, especially those using infrared telescopes that can spot the faint heat of a rogue world, will sharpen our view. Until then, we work with a patchwork of hints, each piece rough around the edges. The models we build are like the old porch boards. Some are warped, some are sturdy, but all bear the weight of our attempts to understand. In the end, the quiet night forces me to accept that some answers will stay just out of reach, like the moth that vanished into the dark beyond the lamp. I can hear the soft creak of the swing rocking in the breeze and the faint rustle of leaves. The porch, the wind, the distant stars, all remind me that the universe is both larger and more intimate than any single theory can capture. A lone firefly flickers near the railing, its glow brief, its path uncertain. The thin metal of the James Webb sunshield drifts in the night wind, a quiet sigh against the porch rail. I sit here, eyes half closed, listening to the low hum of the cooling system that keeps its infrared eyes cold. That hum is a reminder that we are finally able to hear the faint heat of objects that never see a star. Webb's mirrors, coated in gold, gather photons at wavelengths longer than any ground-based eye can catch. In those bands, a rogue planet, just a cold stone floating in space, glows like a faint ember in a dark room. The telescope can separate that ember from the glow of distant galaxies, but it does not always know which ember belongs to a wandering world and which belongs to a distant, dusty galaxy. I find it hard to picture how a single pixel can hold that much mystery. The Nancy Grace Roman Space Telescope will soon sweep a wide swath of the Milky Way, watching for the brief brightening that a rogue planet causes when it passes in front of a background star. That microlensing trick is a bit like watching a firefly flash as it darts past a lantern. The star's light bends, brightens, then fades. Roman's wide field of view means it can watch millions of stars at once, increasing the chance of catching those fleeting flashes. Yet the method only tells us the planet's mass relative to the star, not its composition. We will have to pair the data with other tools to fill the gaps. There are proposals for missions that would travel farther than any telescope we have now. One design calls for a small, solar-powered craft that would drift through the outer solar system, its camera trained on the blackness ahead. Another idea is a fleet of tiny probes launched together, each listening for the faint infrared glow of a wandering world as they coast beyond the Kuiper belt. Those concepts sound like science fiction, and I sometimes wonder if the engineering challenges will outgrow the budget. Still, the thought of a probe that could point directly at a rogue planet and take a close-up measurement feels like a step toward a more direct answer. On the ground, adaptive optics have become far more precise. A laser creates an artificial star in the upper atmosphere, and a deformable mirror bends in real time to cancel the twinkling caused by air currents. The result is a view that rivals space-based images, at least for bright targets. When a rogue planet briefly lenses a star, a ground telescope equipped with this technology can sharpen the light curve, revealing subtle features that hint at an atmosphere or rings. The system is not perfect. Clouds still hide the sky, and the laser guide star can only correct a limited patch of air. Still, each improvement adds a new layer of detail. Gravitational wave observatories have opened a different window on the dark. When two massive objects collide, they send ripples through spacetime that detectors like LIGO and Virgo can hear. Some of those collisions involve neutron stars or black holes that might fling a planet outward, turning it into a wanderer. If a gravitational wave event is followed by a microlensing signal in the same region of the sky, we could link the two, learning how often violent mergers produce rogue worlds. The coordination between these very different instruments is still in its infancy, and I sometimes feel the timing is more hopeful than realistic. Each of these tools, space telescopes, wide-field surveys, dedicated probes, adaptive optics, and gravitational wave detectors, offers a piece of the puzzle. None can solve the whole picture alone. When Webb spots a faint infrared source, Roman may later confirm it by a microlensing flash. A ground telescope can then sharpen the event, while a gravitational wave alert hints at the planet's violent birth. If a future probe manages to fly close enough, it could finally measure the planet's atmosphere, temperature, and perhaps even its magnetic field. The whole effort feels like a patchwork quilt, each patch sewn by a different team, each stitch a small triumph over the darkness. There are still many unknowns. We do not know how many rogue planets drift between the stars, whether most are icy bodies like Pluto or massive gas giants stripped of their suns. The models predict a range, but the data are sparse. I sometimes stare at the night sky and think about the cold emptiness between the points of light, wondering how many silent worlds pass unseen. The answer may lie in the faint heat that Webb can feel, the brief brightening that Roman can record, or the subtle wobble that a laser-corrected telescope can catch. Even the language we use can mislead. Calling a planet free-floating suggests a sense of motion that may not be accurate. Some may be trapped in distant orbits around unseen brown dwarfs. Others might be the remnants of planetary systems that were torn apart long ago. The terminology shapes our expectations, and I try to keep my own phrasing as plain as possible, lest I add another layer of myth to an already mysterious subject. Funding remains a stubborn obstacle. Large projects like Webb and Roman require decades of planning and billions of dollars. New missions focused on rogue planets will have to compete with more immediate concerns, such as climate monitoring or Earth observation. It does not help that the public rarely sees a rogue planet. They are invisible unless we catch them in the act of lensing a star. Without a vivid image, it is hard to rally support. I sometimes wonder whether the quiet work we do will ever be recognized beyond the scientific papers. The next decade will likely bring a flood of data. Roman's microlensing survey is set to begin in the early 2020s, and its catalog of events could number in the tens of thousands. Each event will need to be sorted, modeled, and cross-checked with infrared observations. Machine learning algorithms will sort the noise from the signal, but the human eye will still be needed to catch oddities that the code misses. The balance between automation and careful inspection will be delicate, and I suspect we will still find ourselves at the porch, looking over the numbers with a cup of cold coffee in hand. If a dedicated rogue planet probe ever launches, its success will hinge on a single, fragile instrument. A thermal camera is sensitive enough to detect a few kelvins above the background. That camera must survive years of cold, radiation, and the occasional micrometeoroid. The engineering team will need to test it in a vacuum chamber that mimics the deep freeze of interstellar space. I can picture the moment the probe finally points its eye at a wandering world and registers a signal, a tiny rise in temperature that tells us the planet is not completely dead. That would be a quiet triumph, not a fireworks display. Adaptive optics will keep improving, too. New deformable mirrors with thousands of tiny actuators can correct finer details in the atmosphere. Coupled with larger telescopes, like the upcoming extremely large telescope, ground-based observers will be able to resolve smaller lensing events, perhaps even catching the silhouette of a rogue planet as it passes in front of a distant star. The technology feels like a slow, steady climb up a steep hill, each step measured, each footfall deliberate. Gravitational wave detectors are also planning upgrades. More sensitive mirrors and longer arms will allow them to hear fainter ripples, potentially catching the subtle signals from mergers that happen far from our galaxy. If those events can be linked to later microlensing detections, we will have a chain of evidence that connects a violent birth to a wandering life. The chain will be fragile, but each link will add confidence to the story we are trying to write. In the end, the study of rogue planets is a reminder of how little we know about the dark corners of our own galaxy. The tools we build are like lanterns held up against an endless night, each casting a thin circle of light. Sometimes the circles overlap and we see a clearer picture. Other times they remain separate, leaving shadows where we can only guess. I keep the lanterns polished, hoping that the next flicker will reveal something we have not yet imagined. A moth lands on the porch rail, its wings beating a soft, uneven rhythm. I watch its tiny shadow stretch across the wood, then fade as it flies away.